Hey again, everyone. So we got video installment 3 here, and this is a good one. We're going to talk about something maybe you've heard of. It's called math, and it's kind of outlined really nicely by our little Spider-Man picture here. And the reason I put this in is that all three of these are the same thing, right? We got like 2 times 2. Well, obviously that's 4. We got 2 plus 2. Well, obviously that's 4, and then 2 squared. Well, that's 4. So there's a lot of different ways and different steps you can go about to do the same thing in math, and it's what some people love about math, and it's what some people hate about math. So I'm sorry, no matter kind of which category you're in, because math sometimes just got to get some math done. And so before actually going into these problems themselves, I'm going to talk a little bit about simple harmonic motion and how we're connecting, whether you know it or not, last unit to this unit, as well as to unit 1 of the whole school year, and as well as kind of pointing out the equations that you will have for the AP test. So I want to first actually just look a little bit at the equation sheet. And so I think you have this on page 2 in your notebook. And we've kind of gone through and we've used most of these actually already this year. And the ones we didn't get to, like, we're just not going to deal with. Like all this, like, you don't got to worry about any of that because none of that's on the AP test. Same with this one, even though you've probably seen it in Science Academy about waves, which would have been our next unit. So really talking about this unit, we so far have got this equation kind of describes a simple harmonic oscillator. And we've also been told that, well, the period is the same as the inverse of the frequency, or rewritten, if I multiply by f and then I divide by t, these kind of just essentially switch spots. So then we have the frequency is 1 over the period. And so what that really means is that in this equation here, this little f right here, you could swap out for 1 over t if you want, and you end up getting the same equation. They're just giving you this one version for the AP test. Kind of like how we had these three, we had these 3 equations in unit 1, and they're only giving you these 2 of them, even though they should have given you all 3. It's just what they chose to do for whatever arbitrary reason. So sorry about that. And this kind of part I just put here in purple is this. Now, it may look weird that there's this middle part, this 2 pi over omega. Like, what the heck is up with that? Where did that come from? Because the left side and the right side, well, that's this stuff we just kind of looked at together. It turns out that we can relate things that are going back and forth, like a spring with a mass on it, whether it's going horizontally or vertically, or pendulum swinging back and forth, as something kind of rotating through like a circle. I know that sounds weird, but I'll show that in a moment. And then the other thing is that we've been given these 2 other equations where really, and you could write this on your AP equation sheet, S is for a spring, because a spring can have a different size mass on it and a different size spring constant. So that kind of makes sense. And we get that if the spring is really strong, that means this K thing is really big. Then if we're dividing by a very big number, we'll get a small answer on the right side. And that means it'll go back and forth really quickly. And that makes sense, because if you had like a really strong spring and you pull it and you let it go, it's going to bounce back and forth really quick. And then the P, you maybe have guessed, is for a pendulum, where that's really it. The other thing that's kind of mentioned is, well, there's this restoring force for springs, and this is from way back actually, but it's kind of coming back now. And in the videos you watch, they put a negative sign here, and they didn't have these absolute value bars. And the negative sign really just kind of meant that it always goes opposite how you displace it. So if you give it a positive x, the force is going to be in the negative direction, so opposite it. If you give it a negative x direction, well, if you pull your spring in whatever you call the negative direction and you take the negative of it, well, the force is now positive. So really the negative just makes sure that the force and where the mass is on the spring are always opposing each other. The spring is always making it go back to equilibrium, is really all that means. And then kind of just some side ones that are kind of tangentially related. Gravitational potential energy is this. So if your pendulum swings up some height y, we could kind of use that. Or if your spring, we're talking about the energy stored in it, we can kind of use that for it. but that I think Roy should kind of sum it up. So these are kind of the big equations for this unit, mainly these first four with this x, and then with our period equation, and then for the spring and the pendulum. Now, if you're feeling pretty good with this, skip ahead a couple minutes and see me actually looking at the problems themselves. But I want to kind of do a little recap so far of where we're at, in case you've been watching these videos and you're like, "Gah, watching videos and not being able to ask questions sucks. I don't know if I'm getting it or not, but I'm scared." So I want to relate this simple harmonic motion you've been watching videos on so far to circular motion, which we're used to. So it turns out that we've been looking at like a mass on a spring, and the mass will kind of go over here, and then it goes, and then it'll go over here, and it'll go faster and faster through equilibrium, and then it'll slow down as the spring gets squished, and then it stops, and then it goes back and speeds up, and then it'll start slowing down as the spring stretches, and it'll stop, and it'll keep doing this back and forth and back and forth. So that's the gist of it so far. Now, the neat thing is that if you had, like, I don't know, some kind of just spinning turntable hooked up to a motor or something, you would end up finding out that if you had a projector up above and there's light shining down on it, we can kind of see our little beams of light here, all kind of shining down uniformly. We're going to get a shadow of the ball. And the farthest the ball's shadow will be is when the ball's over here, and it would be right there. Or when the ball's over here, so when it would be right there. And so we end up getting that this shadow just goes, well, back and forth and back and forth and back and forth. And the shadow itself would actually be undergoing a simple harmonic motion as well, where it has some maximum amplitude and some like negative amplitude, and then some equilibrium point as well. And so because of this, we could say that, well, this ball is rotating at some angular velocity omega, that, well, we could actually treat the ball as having a frequency as well. Because if we know that the time it takes, or that the angle it goes through is theta, well, we know that omega is the change in theta over the change in time. And so we can really just kind of treat it the same way. And that's where this part came from. Now, you haven't had to use that really on any of the questions so far, and it doesn't seem to be a very big thing on the AP test. I actually have never seen a question specifically relating to it, but because it's on the equation sheet, it's good to know that you can relate kind of an angular frequency to frequency, and that's really kind of what this omega is now called. We know it's really angular velocity. It's how quick it's just going. But in a similar way, it's kind of like how quickly something goes back and forth. So kind of keep that just in mind, I guess, really. So similarly, if we think back to our ticker tape timer lab, with our ticker tape timer with the ticker tape that tick, 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 tick over and over and over, right? And all it did is it just put down dots. And our ticker tape timer put down dots, and it put down 60 dots every single second. No matter how fast the cart was moving or how fast you pulled the tape, it put down 60 dots every second. And so if it's moving really slowly, well, the dots are going to be really like stacked on top of each other. But if it's moving really quick, well, the thing is going to be moving and the dots are still going down at the same rate, and we're going to get more spacing of the dots. And so this is really where we can kind of see how these graphs form from our simple harmonic oscillators. This is kind of the best analogy and depiction I can show for it. And so if we think about it, if this object was pulled back to A, and then, or actually if the object was pulled to negative A and let go, and then it moves through equilibrium, and then it moves to here, and we start our ticker tape timer, so to speak, and it just is making dots, and it's making dots at the same rate every single second. We'd find that, well, as our box slows down, well, the dots are going to be right there on top of each other. And then as the box stops here, well, they literally would be on top of each other for that instant. And then it turns around and starts speeding up as it goes towards that equilibrium. So it speeds up and the dots get more and more and more spaced apart. But then once it passes through equilibrium, the spring is actually going to start resisting its motion, because you're compressing the spring and it's going to start pushing back you towards equilibrium. It's that restoring force. We start seeing that the dots get closer and closer and closer packed together here. And so it repeats over and over and over and over. Now, the neat thing about it is really this amplitude is just our displacement. It's where the box is at. And in its own kind of weird regards, the dots really are the same unit of time. So really, this axis here is our x, and then this axis here is really our time. And so if you took this and you spun your screen around, you would literally see this graph. And so my mathy folks, people that have seen kind of some trig a little more, especially my folks in calculus, you've seen, oh, well, we're looking at sines and cosines now. And we see, well, cosine is a max when it's at 0. So this is a cosine currently because we just chose to start taking dots here when our box is maybe at this maximum amplitude right here. Now, if we chose to take it when our box was instead of here, our box was over here, well, our dots would start down here, and we kind of get the reverse graph of it in essence. Now, if we chose to take it at equilibrium, it depends on whether it's going to the right or to the left, but it was going to the right, well, we would get this kind of graph, and this would actually be a sine graph for it, or it could be going the other way, and we would get a negative sign. So that's just kind of how we go and can represent, oh, this thing moving back and forth really as this sine or cosine graph, which is kind of odd, I know. And even more so how it kind of relates to things rotating and going in circles. Now, the last thing I want to mention, and here my calculus folks, you have a little bit of an advantage, but I guess you've put in the hard work to struggle through calculus, is going immediately from this position graph to this velocity graph. Now, for my calculus folks, velocity is just a straight derivative of position. So if you have a cosine graph, you're going to get a sine graph or a negative sine graph more specifically. And so it really is that easy for my calc folks. For my non-calc folks, I'm going to really just explain what that sentence to my calc folks meant in non-calculus terms. So if we look and we keep in mind that velocity is the slope or the change in displacement over time, well, the slope right here is 0. So we start at 0. The slope right here is our maximum negative. So I go down to our maximum, Vmax negative. Our slope here, 0 again. Our slope right here, our maximum positive. And so all I'm doing is I can actually see that, oh, these kind of match right along the line. And then if my slope right here is 0 again, and this is how you would actually get this green graph if I just gave you a blank axis, really. You go, oh, well, the slope here, well, that's 0. And I know I am aware that I skipped one. Here, it's maximum, but it's going downhill, so it is negative. And so from this, you can see that, well, we get this beautiful kind of green curve that's going on here. And since it is starting at the origin and it's going negative, this would be described as a negative sign as we have right there. So that's actually how to go from the displacement graph to the velocity graph. And it actually works in reverse as well, which is kind of spooky to think about. If we kind of took all of this and like got rid of it, actually, you could totally do it in reverse. If I said, here's the velocity graph, give me the position graph, well, you'd have to go, oh man, well, let me think about it here. Well, the slope is steepest right here because it's actually steep. It's kind of going that way, right? So you go, well, it's steepest there, and so we're going to have some maximum amplitude. And if I look right here, well, I'm actually at my maximum, or my slope, really. Maybe that's the better way to think about it. Sorry, I was thinking in derivatives again. Where I'd say, well, my slope is at 0, or my value is at 0, which means the slope of this one must be 0. So either I'm starting here or I'm starting here. I'm not sure actually yet. But I can see that, hey, here I'm at my maximum negative value. So how do I go from 0 to a maximum negative? Well, to go from 0 slope to a maximum negative, I'd have to start up here and curve down. Otherwise, I'd be starting here and curving down. So then I go, well, I look over it here, and not the slope of this anymore, but just the raw value of it. Well, I'm at 0 again. So my slope has to be 0. So we're going from a value or a value to a maximum negative to that same value again, so 0 to maximum negative to 0, well, 0 slope to maximum negative to 0 slope again. And we can actually work in reverse the same exact way, which is kind of neat. And then we could actually do the same exact thing and get the acceleration graph. Kind of neat. If we wanted to look at that one, we just have to look at the slope of this. And so we'd find that, well, if I go right here, and I'm just kind of zooming in, looking at my velocity one now, well, here, my slope is its maximum, and it's a negative value. And then I go in right here, and I find that, oh, my slope is a 0, and then my slope is maximum positive, and then I have 0 again, and then a maximum negative, and then 0 again, and then a maximum positive, and then 0 again, and a maximum negative. So as I'm kind of looking at these, I can go, well, how does my graph have to look then? I have some 0 or some maximum negative. So I'm here, let's call it right here and right here, try and keep those just eyeballed about the same distance apart. And then I have 0, so I'm at a negative, and then I'm at 0, and then I'm at this maximum positive, and then I'm at 0 again, and then I'm at my maximum negative, and then I'm at 0, and then I'm at my maximum positive, and then I'm all the way to 0 again, and then I'm at my maximum negative. And so going from the slope of this, I can see that, well, we start at maximum negative, so we're going to go just like this. And so the weird thing is it actually looks a lot like this first one, but it's just flipped. So we end up having this kind of nice symmetry that if this is a positive cosine, our acceleration becomes a negative cosine. So the way that we would actually write the equation, my calc folks maybe can kind of think on this a little bit, but our acceleration as a function of time would be, and since it's starting as a negative, we're going to have our negative a max cosine of omega t, which really kind of using our equations as we were using it here would be cosine of 2 pi ft. So negative a max cosine of 2 pi ft. Okay, wow, that was more than I was expecting to go into, but I hope that helped a little bit. So let's do some math now. So we have a block, it's on a spring, it has some frequency of 2 hertz, it has an amplitude of 0.25, we're given our k value. What is the mass of the block? So we want the mass of the block. Well, there's really only one equation we even had from earlier that even has mass in it. It's that one, and it's the period for a spring. Now, we weren't given the period, though, in this question. We were given the frequency in this question. So we can write out our equation, have that, well, the period for the spring, it's that 2 pi mass over, or square root of mass over the spring constant. And we know that the period is 1 over the frequency. Well, we were given the frequency. So if I know the frequency, I can actually get this period for my spring now, right? Now amplitude. I don't even think I need amplitude. I'm looking at this. There is no amplitude in any of these equations. That's kind of crazy to think about. It doesn't matter how far you pull this little block out. It could be way over here. And as long as the mass of it's the same, and the spring is the same strength, and it doesn't get stretched too far, it's going to go back and forth at the same rate. That's kind of neat to think about. Even though it's going farther, it's actually going to take the same amount of time to go one full cycle. And that's kind of weird. That is. It will be going a little faster here because it has to cover more distance, but it actually will take the same amount of time. So we're given the spring constant. We know K. We know the frequency. So, well, if the frequency is 2 hertz, doesn't that mean the period here is 1 over 2 hertz? So that's really just like 0.5 seconds. We know the period now. So if I know the period, and I know K, I can get M. Now, I don't like plugging in the numbers and having to do algebra with numbers because I screw up with numbers. It's easier for me to make sure that an M stays an M rather than have a 0.5 not turn in accidentally to a 5 because I forgot the decimal. So I'm going to just simplify this with some algebra. So if I divide by 2 pi, we have TS over 2 pi is the square root of M over K. Kind of checking you on your order of operations here. Now we have to square root both sides to get rid of the square root. And then if I get rid of the square root on the right side by squaring everything on the left, I would just have to multiply by K. So then I have T, or the period for the spring, squared over 4 pi squared is mass over K. Well, we want the mass, so I just need to multiply by K. So I'm just going to get rid of that K, multiply it over there. So now I just have to put this all into the calculator because we know the period and we know K. So for me, I have my calculator right here at home, but maybe you don't have yours. So I'm going to show you both. And I'm going to actually just show both of those. So we have to use spring constant times the period squared over 4 pi squared. So I'm going to switch over to my camera right here. Let's see if it keeps on the camera. Oh, sweet. There's my socks. Let's go up a little bit more. So we have our spring constant, and I'm already forgetting what our spring was at. I think our spring constant was 75. So I have to do 75 times, and it was our period squared, and our period we said was 0.5. So 0.5 squared, and then we're dividing that by 4 times pi squared. 0.47494. Okay, now I don't get that many significant figures. I think it tells us to use 2, so my answer would be 0.47. Now, maybe though, you don't happen to have like a nice physical calculator right with you. So how the heck would I do this on the calculator? Well, it's going to be almost the same thing. So I went and just typed in Google Calculator, and this pops up, and I want to just clear it. So I'm going to have to use some parentheses. We're going to do the same exact thing. So I have 75 times, and then my period squared, 0.5, and then we go squared, and then divide it by 4 times pi, and then I have to hit this little x with the y above it, because the pi is my x, and now that's squared, and I got the same exact answer. Perfect. So when it comes down to it then, my answer that I have to put down is going to be 0.47. Now it says no units, so forget units. But the mass would be in kilograms, but again, we're not putting units. Now you also could have written this as 0.47 because the 0 before decimal doesn't count. So these both have two significant figures. So we're going to speed up a little bit now because from this point on, the questions are actually very similar. You're just solving for different things. So we have 2 kilograms. We know the mass. And we know the amplitude, but didn't seem to help us at all last time. Maybe it will this time. We have the spring constant. What's the period? So it's asking us to find big T. So that actually, this is probably going to be an easier problem than the last one because we don't have to do any algebra to get the period for the spring alone. We just have 2 pi square root of M over K. We know M, we know K. So I just have to poke into my calculator 2 times pi times 2 kilograms over 85 Newton meters. Well, I go and poke that into my calculator. 2 times pi times the square root of 2 divided by 85. And I get 0.96380. But we want two significant figures again. So my answer is just going to be 0.96, or I could have been 0.96. But again, I can't put any units because Google Forms doesn't know how to assess that your units are correct. So looking at our next one, we again 2 kilogram mass. So we know M. Well, that's not an M. That looks like a weird N. And it says ideal spring. Let me just mention that for a second here. Ideal spring. an ideal spring. So the spring is really like this curly, Q-y looking thing, right? Now, oftentimes when you have a spring and you're going to take the thing and you actually like squish it together or you stretch it way out, what happens is there's actually some friction in the spring itself. And so a non-ideal spring is just going to lose some energy through the fact that there's friction like as it heats up. Like if you ever have a paper clip, and I would challenge you, if you have paper clips at home, go get one and just start bending it back and forth and back and forth. It'll snap, and once it snaps, you touch it, it's warm actually where you touched it because there's just friction in the metal itself. Now an ideal spring has none of that, so that's what this blue part really is about. And we're given the amplitude, we're given the spring constant, we want to find the frequency. Great. So we know it hasn't been useful so far. Maybe it finally will be. I don't know. And we know K, and we want to find the frequency. So again, since we don't have pendulums here, we probably won't need the pendulum equation over here, but maybe we will. And we still have 2 pi square root of m over K. Now we know m, and we know K. So I can get my period instantly just like that. But we don't want the period anymore. We want the frequency. So how do I get that? Well, we have to know that period and frequency are just inverses of each other. It's just period or the frequency is just the reciprocal of the period. So if I can get the period, I can put it right in there and get the frequency. So that's all we're going to do. So period for my spring is 2 times pi times my 2.0 kilograms over my 85 newtons per meter, whatever the heck that is. So let's use a little more practice with the Google calculator just to get a little refresher on it. So we're just trying to find that period. So we're doing 2 times pi times, and now the square root of 2 divided by 85 equals, so 0.96. Oh, that's what we just got before. That was the question we just solved. And now I want to do 1 divided by that. So let's make this a 0.9637 or 0.964, and then we'll kind of round at the very end properly. So we're really just having to do 1 divided by this to get my frequency for it. So 1 divided by 0.964, I get 1.037. So let's look at the question again. So the question says round to 3 significant figures. So if I want to look at that question or the answer we got, well, 3 significant figures, that would be 1.03, but this 7 makes that 3 become a 4. So 1.04 is our answer. So 1.04, and there is no other way that would be correct to actually write this. And if you're like, whoa, I didn't get that, I lost that, I think go back to, where was it, page like 16 actually, the beginning of unit 1, where we did our significant figures, and just kind of it's one side of one sheet of paper, just kind of glance at that, what I would recommend. So now 0.8 kilogram mass, we have M attached to some ideal spring. Honestly, it's horizontally. Okay, that's kind of neat. We're told that it goes sideways this time. And we're given the period. So what the heck could they be asking us to find? We're given an amplitude. It seems useless. Okay. Oh, what's the spring constant? That's what we want to find. So this one, okay, this one's a little different. So really, this is just some algebra. I'm checking you on, can you do algebra? And that's what this unit actually has a lot of, it seems. Because if the period of a spring is this guy, well, I want to get K. So I can kind of skip and do a couple steps at once, but let's kind of simplify. We want to get the 2 pi over first. So our period for a spring over 2 pi is equal to m over k. Well, if I want to get the k alone, I need to square everything first. So I'm going to get rid of that. Well, let's keep that there. So if I square both sides, the square root's gone on the right side. Oops. Let's get rid of, will let me, oh, it does work. So we've gotten rid of that, and we've had to square everything on the left side then. So that's squared. This 2 becomes a 4, and that's squared. So now I need to get k though. So I'm going to multiply k over to the left side. And maybe you're like, I don't get what you mean multiply k over to the left side. I was just taught this a way that I think differs from some folks. Really, I'm multiplying by k on both sides. And I know that these two cancel. So really, in essence, this whole process that maybe you're used to seeing it as is the same exact thing as I'm just going to take this k and multiply it over there because we know it's going to get canceled on the right side anyways. So if I do that, oops, there we go. If I multiply k over, well, now k's with all this other like crap on the left side. So now we're going to have to get rid of all that. So now we have k period for the spring squared over 4 pi squared is equal to m. We don't want m. So now I have to multiply by 4 pi squared over to this side and divide by the period squared over to that side as well. And so really I'm going to get that my spring constant is equal to 4 pi squared m over the period squared. And we were given the period and we were given the mass. So really it's now just the calculator part. So I'm doing 4 times pi squared times my mass of 0.80 kilograms divided by my period is 0.5. Don't forget to square it. I get 126, but it says 2 sig figs. So really 126, that becomes 130. And you better not put a decimal because that would be 3 significant figures, while that's 2 significant figures. So there we go with that one. And now our last one, we have a 1.5 kilogram mass. We know m, spring, it goes horizontally. We're given the amplitude. That's worthless. We've gotten that now. And it has some spring constant of 85 Newton meters. Actually, well, the amplitude isn't useless. When we're looking at graphs, the amplitude will be helpful because it will let us know how far something has gone. But as far as finding the period or the frequency, then I would say the amplitude is kind of worthless. And we're trying to find the period of the motion. So this is actually kind of one of our easier questions. Again, we have period for the spring is 2 times pi times the mass over the spring constant. And so our mass is 1.5 kilograms and our spring constant is 85 newtons per meter. So I need to put this all in the calculator. So we clear it. We're doing 2 times pi times the square root of 1.5 divided by 85, and I get 0.83467 blah 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 blah. So looking at the question, it tells us to use 2 significant figures, and so I have kind of 2 options now. I could say 0.83 and the period, so it actually would be seconds, but we know we cannot use units here, or 0.83. Both of these have 2 significant figures. So that's it for our third video. I hope this is the longest one. I'm sorry if you're just sick of my insufferable voice. So until next time.